So the exploration exploitation dilemma, is quite concrete here. So you want to best food, so how do you balance this? A really popular example at the moment, this is like a big application area with lots of resource being put in by Yahoo, well, the ex-Yahoo guys, Microsoft, Google, and so forth, as for online advertising. So it started off with online banner advertisements, and now it's expanded to all kinds of decision-making on the internet. And so the idea is that, when you're faced with some page and the website is basically deciding what advert to show you as a user. And the question is, should they show you something, the advert that's been most successful, that's had the most people click on it so far, or should they explore, because maybe there's some adverts that just haven't been shown very much and they don't know yet which of those adverts is going to be the most popular until they try them enough. So again, they have to trade off exploitation with exploration. So we'll see more of this in the contextual bandit setting. There's often some context here basically means knowing something about the users. Oil drilling. So I used to work in Alberta in Canada, where this was actually a big deal. People cared about things like this. So exploitation might mean something like drilling at the best known location. So you drill for oil in a bunch of different places, and maybe you found a certain amount of oil or a certain quality of sand that has a certain amount of oil that's been extracted. And so it's quite expensive to drill for more places, but at some point you might want to drill at new locations and find a better spot. So you need to again trade off the expenses of these various things. Finally, game playing might mean that exploitation might mean you're playing against some opponent, you've got some idea of which move you believe is best. You don't really know how this opponent's going to respond, and so maybe occasionally you want to try a different strategy, play an experimental move and find out how they respond to that move. So these are all examples of exploration versus exploitation. Okay, so let's make this concrete. We're going to come up with a very simple formalism called the multi-armed bandit, which will explore most of the key ideas for exploration versus exploitation. And it looks something like this. So we've got some octopus here playing a bunch of machines. This is where the name comes from. So these are called, in the States at least, one-armed bandit machines. These things where you pull and you either get some reward from it, some payout with some probability or not. And the point is that each of them might have a different payout. And so you want to kind of keep trying all the different machines until you find the one that's got the best payout rate. If you're in a real casino, probably the right thing to do is just stop. But we're imagining that some of them might actually pay out more than you put in. Okay, so we're basically going to simplify down our MDP to just two things. There's just going to be an action set, A, and a reward function, R. So A is the set of arms that we've got that we can pull. So they're just called the actions, or arms in this terminology. And now we're just going to have a distribution over rewards that just depends on which action we pick. So essentially the way to think about it is that each one of these machines might have some unknown reward distribution that determines how much money you're going to get from this machine when you pull that arm. And if this distribution can have any shape, it could be, it could be anything. And so there's some probabilistic reward function here. And now, at each step, what we get to do is we get to pick one of these arms, we get to pick an action, pull one of these machines, and we get to observe the reward just for that arm. We don't get to see what happens from any of the other machines, only one that we pick. So it generates a reward according to this distribution, and now the goal is to maximize cumulative reward. So this is very familiar from the rest of reinforcement learning. It's just that we've taken out the states and the transitions from states to other states. So it's a simplified version. We just want to maximize the total reward we get at every step. Okay, is that clear? Right. So we're going to take a slightly different view just on the way that we measure reward. And we're going to talk about something called regret here. So it helps us really look in some principled way at how good a particular exploration strategy is. So first of all, we can define the action value. So this is just like the action value function we had for the MDP case, but there's no state, so it's just Q of A. So this is basically the expected reward that we'll get, so the mean of any one of these machines. So each of these machines has some mean payout, and this is the true mean, this QA. And we're going to estimate this thing later, but for now this is the true mean. Okay. And then the optimal value that we can get is basically the value of the best arm that we can pull on. So we're just looking for this A star, and that's the best value that we can get by playing this particular multi-arm bandit. And what we call the regret is how much we really regret choosing a different arm to the optimal one for any given step. So at any given step, time step t, we might pick action 80, and the difference between the optimal value and the value of the arm we actually picked is this regret here. So we're just looking at the means here. So this is, it doesn't matter what the noise was in that particular instance. We're looking at the mean of what happened if we picked that particular action compared to the best mean that we could have picked. So this is the expectation here. And that's what we call the regret. And then the total regret is basically just summing this up over time. So this is over all the action selections that we picked, all the way up to the current time step t, how much have we regretted all the different decisions that we've made? How much opportunity loss was there compared to the best decisions we could have made? So if we really picked the best thing at every step, we would have got V star at every single step. That's the best mean we could have got on average. But we picked some other actions, and those other actions on average will give us some, so there might be some other strategy, and if we pick those other actions, then in the mean there's going to be some opportunity loss. And what we care about is minimizing this regret, this total regret. So a good strategy is something which minimizes this total regret. A good exploration and exploitation strategy is one that gets as many actions as possible that are close to the best actions, to the best values. And over time we want to get closer and closer, so we want this total regret to go down. And so if we want to maximize the cumulative reward, that's the same as saying we want to minimize the total regret, because the best we could do is to find this V star. And so if we ever get down to a regret of 0, then we're basically picking actions according to the optimal strategy to achieve the best we can do in this particular pattern. Okay, so just to get some insight into what this regret is then, so what we're going to do is just count the number of times that we pick a particular action here. So this is what we call NT, so this is the number of times we picked a particular arm A. And what we're going to do is look at the gaps. So the gap is basically the difference between how well we could have done, so this is the maximum we could have got, compared to what happens for that particular action there. So there might be some arm that we could pull, which gives us a reward of 3 less than the best action. So we would say that the gap between the best action and that action is 3 in that case. And then the point is that this regret just depends on the gaps in the counts. So if we want to work out the regret, basically the total regret, it turns out, because we're looking, remember, the total regret is like this total opportunity loss between the best we could have done at every step and what we get from picking a particular action. And so all that really matters is how often we pick that particular action, which is this count here, multiplied by the gap for that particular arm. So if we pick arms with big gaps a lot of the time, we will have a big regret. If we pick arms with small gaps, then we will have less regret. And if we pick arms with 0 gaps, then we will get 0 regret. So the bigger the gap is between the action we pick and the best possible thing we could do, the worse our regret gets. Is that clear? Okay. So what we try to do is find algorithms for exploration that sort of ensure small gap counts for large gaps. That's the goal there. We basically want to make sure that we don't waste many trials on actions that have a big difference from the optimal. Again, there's a problem so far that we don't know these gaps. I mean, we don't know the reward setup. If we knew the gaps would be done, we would just pick the action with the smallest gap. So we need to be a bit clever about how we do this. And so now we're going to start to talk about strategies for doing that. But, okay, so I really kind of want you to have this picture in your mind when we're talking about regret. So this is sort of a plot where, probably can't see the numbers at all. Anyway, numbers don't matter. This is like the number of steps that our algorithm is taking. Okay, so this is, each one of these is like a pull on one of the arms of this bandit, and then we're measuring the total regret up here. And now what we want to know is, for any given algorithm, what's the shape of this particular curve? How does the regret accumulate as we try more and more arms? And what we'd like is something that has a shape a bit more like this, where maybe we do a bit of exploration early on, we lose a little bit of potential reward to begin with, but ultimately it's sort of sublinear, in the amount of regret that it gets. And what we're going to see in the next few slides is that the sort of standard algorithms we've been looking at, like greedy and epsilon greedy, they have linear regret. In other words, no matter how long you keep exploring, you're just going to keep on incurring opportunity loss after opportunity loss, and you'll never settle down, you'll never end up getting sort of less and less regret. You'll still incur opportunity loss forever. Whereas if we're clever about it, this is one example of a slightly cleverer algorithm, and we'll get to some better ones later, then you can actually get this sublinear regret, which is actually logarithmic in the number of steps. So the goal is to find algorithms that look a bit like this. So we want to play them. As we play it more and more, we get sort of less and less regret about what happens. Okay, so just a bit of intuition about this. So why do we get greedy and epsilon greedy looking like this? The basic idea is that if an algorithm keeps exploring forever, then every time it explores, there's some regret that gets incurred because there's some probability that it will pick a bad action. And so every step, there's some small probability, this, like epsilon probability for epsilon greedy, but at each step it will cause some regret. And if it never explores, it will also have linear total regret because it can get stuck on a bad action. And so in expectation, you can end up looking like this. Let's make that concrete. Okay, so let's do greedy first. So greedy, basically what we're going to do now for the remaining part of this is we're going to imagine that we're actually estimating the action value function. So we're just assuming that we're just going to do something like taking the mean of the actions that we've seen, the rewards we've seen so far for each of these actions. So the simplest way to do that would be Monte Carlo evaluation. In other words, for each action we want to figure out, well, how good was that arm? Well, the simplest way to do that is just to take the mean of all the rewards we've seen when we've taken that action. So that's all this is doing, it's just picking out, this indicator just picks out all the times that our action selection actually matched A. And amongst all of those, we average the rewards that we got, and we can just divide by the count of the number of times we actually picked A. So this is just the mean, the empirical mean of all the times we pick action A. So how good is action A? And then being greedy, well, what does that mean? Well, that means that we select the argmax of this thing. So that's the sort of strategy that we already sort of know is naive, because we can lock on and get stuck on something. And because we never explore, we can just get stuck on the wrong value. And so what that means is that if there's some non-zero probability that we get stuck on the suboptimal action forever, so let's say there's a 0.1 probability of getting stuck on the wrong action, that means that we'll have linear total regret, because at every step, on average, there's 0.1 probability that we've got that wrong action. Okay. Now, epsilon greedy, so that continues to explore forever. So we have this idea that with probability 1 minus epsilon, we select the argmax. So with 1 minus epsilon, so with, say, 90% probability, we pick the greedy action. And with 10% probability, say, we select a random action. But because this is constant here, that means that we're always going to be getting some minimum regret. So the regret at each step is basically going to be, so there's some probability epsilon divided by the size of the action space that will pick any given action. And there's going to be some gap for that action. And so we're always going to have some regret that's basically a function of these gaps. Every single step we're basically getting some regret that's basically like the average gap size. And because we continue to explore forever, we're just going to get this again and again and again. So again, we get linear total regret. So we've basically seen why we have these two lines here. So these two lines, they're bad. In the long run, you just either do not enough exploration or too much exploration. So now we're going to consider the first one, which looks like this. Okay. So it's a natural idea, okay? So we've seen that if you explore too much, then if you continue to explore forever, then you just keep incurring regret. But if you don't explore enough, then you can lock onto the wrong thing. So a natural idea is to decay epsilon over time. Okay, so we're going to come up with some schedule for epsilon, and basically going to reduce epsilon according to this schedule. We're going to do epsilon greedy at every step, but we're going to change the value of epsilon. So here's one schedule that actually works and gives this nice property. And the idea is that there's this sort of magic numbers involved. So you shouldn't think this is a practical algorithm. This is just an illustration that this is possible. So there's some magic numbers involved which depend on the gaps. So if you know the gaps, you can come up with this magic schedule. And according to the magic schedule, we then achieve this logarithmic total regret eventually. So there exists a magic schedule, but we need to know the gaps to figure out the magic schedule. Okay, so this is not a practical algorithm, but it does illustrate the idea that we can get closer to what we want. So our goal so far then is we want to get something which looks a bit like this, that gets this sort of logarithmic regret. And we want to be able to do this for any multi-armed bandit. It doesn't matter what the distributions are, we want to be able to do it for anything without knowing what this R looks like in advance, without knowing anything about the gaps. So that's sort of the goal of what we're doing here. Now it turns out that there's this it turns out there's a lower bound on how well we could possibly do. So there's a proof which basically says that depending on, so if you think about what's the hardness of the problem, what makes a multi-armed bandit problem harder, or what makes it harder or easier, is basically how similar the optimal arm is to the other arms. So the way to think about that is that a hard problem is one that has very similar looking arms that have different means. So the probability distributions sort of overlap quite a lot for these two arms, but their means are quite different. That's the hardest kind of problem, because it means you can be misled into thinking that one arm is better than the other by some of the noise in those things. So imagine that there are two arms where, you know, for 100 steps they both give exactly the same value, but then on the 100th step, one of them gives a massively lower value than the other one. Okay, that would be a very hard problem, because you need to see a lot of data to figure it out. Okay, so this lower bound then just depends on the gaps, which is how similar the means are, and the KL divergence between the distributions, which is how similar the distributions are. And so, you know, the details of this don't matter too much. It's just that there is, so this is a proof to say that you can never do better than this. So the amount of regret, we can't ever hope to beat this bound here. So there's a lower bound that says that the total regret has to be at least logarithmic in t, so this is like giving us the shape that we were interested in. So the log t term is basically this shape here. So we know that it has to have roughly this shape here, and that the constant depends on something which is proportional to the gap sizes and inversely proportional to the KL divergences, which is exactly this hardness idea. So the bigger the gaps, the harder the problem, the bigger the regrets are going to be. And the smaller the KL divergences, the more similar these distributions look, the harder the problem's going to be and the regrets will be bigger. Okay. Right. Right, now on to some algorithms. So I'm trying to lead up to what's basically considered is the most widely used algorithm for multi-armed bandits and many, many other settings. It's very popular. So this is all leading to that. So it is useful to understand where this comes from. So there's a very important principle, which is called optimism in the face of uncertainty. And the way to think about that is to sort of look at something like the following diagram. So imagine that you are sort of tracking not just the mean, not just estimating the means of your actions. Imagine there's 3 different actions you could pull. So there's three arms you could pull. And we've seen some data on these arms, we've seen some rewards from each of them. But perhaps we've pulled this green one a few more times than the red one, and we've pulled the blue one least of all. And so now if you're going to estimate the value, you might say, well, there's some, not just a mean, but there's some whole distribution over what the values might be. So if we were going to sort of plot out the PDF for each of these arms, we might estimate the values look like this. We might say, okay, well, this green action here has a mean of something like this, but maybe the value's a little bit higher, and maybe the value's a little bit lower. We've got a pretty good idea of what this green one is. We've maybe played it 10 times or so. Whereas this blue one, perhaps we've only played it 2 or 3 times, so we've got a mean which is somewhere over here, but for all we know, the true mean might be way down here, or it might be way up here. Okay? So the question is, if you have these 3 distributions for actions, which one should you pick? So which one would you pick? Maybe we'll do a hand show. So who would pick the green one? Okay. Who will pick the red one? And who will pick the blue one? Okay, interesting, quite a good mixture, which shows that we need some guiding principles to help us to figure out what the right answer is. And the right answer is very hard. It all depends on exactly the right shape of these. So, but the intuition that we're going to use here is basically something called optimism in the face of uncertainty. And the principle basically states that the more uncertain we are about an action value, then the more important it is to explore that action. So in that case, that might suggest to us that we pick the blue one in this example, because the blue one has the greatest potential of turning out to be the best action. It might turn out that if we ignore this blue one and we never try it, we might have an enormous regret, because it might turn out that the actual value of this blue one is somewhere up here, in this tail region here. And if we don't ever try it and don't explore it at all, then we might really be missing out in a big way on the best one. Whereas the green one, yeah, sure, we could pick that green one and we'll get, that's exploitation. Picking the green one's exploitation. And so we need to mix these things. We need to have the right mixture of exploitation and exploration. But the idea of this principle is to kind of pick things according to something about their upper bound, not something about their mean. So what we're going to look at is ways to basically compute the upper bound of these actions. So sort of estimate and say, okay, well, the upper bound of this blue one is maybe over here, the upper bound of the red one's maybe over here, and the upper bound of the green one's maybe over here. And then pick the one with the highest upper bound. Okay. So we call these upper confidence bounds. And so what we want to do is estimate an upper confidence bound for each action value. And so what we want to pick is basically, we want to be able to say, pick a value such that with high probability, we know that that we're not going to be wrong, but that the mean doesn't sort of fall outside this region. So for example, for the blue one, we want to say, let's say we want to say this with 1% probability. We want to find the value such that we're 99% sure that the mean sort of lies over here. And it doesn't lie, that basically there's less than a 1% probability that it lies beyond this region here. Okay, so we're going to pick an upper confidence such that the true mean is less than our upper confidence bound with high probability. Okay? And so this depends on how many times we've actually picked that action. And so if we haven't seen an action very much, then that basically means that the estimated value is very uncertain, and so we need to pick that action more, so it's going to have a large uncertainty, and so we'll end up picking it more. And if we've picked an action a lot of times already, we'll have a small uncertainty, the distribution will be narrowed, the estimated value is very accurate, and so we want to basically add on a smaller bonus there. And then the idea is we simply pick the action that maximizes this UCB. So we take our mean, and we add on this UCB term, like a bonus saying how uncertain we are about it. Or we pick the action with the highest sum of the mean plus the bonus. Okay. So there's going to be one more piece of maths to get to the famous algorithm, and then the rest of it is going to be a bit more informal again. Okay. So there's a very well-known theorem called Houghton's inequality. And basically what this thing tells us is there are many, many ways to bound this. This is a quite reasonably tight bound on what's the probability that the mean of some random variable, the true mean of some random variable, is greater than our empirical mean plus some amount. So here we've got some random variables, we've seen some examples of those random variables, so we've seen a bunch of numbers, we take their mean, and what's the probability that the true mean is much bigger than the empirical mean. And it turns out that the probability can be bounded by this e to the minus 2 tu squared here. So we're basically going to use that idea to figure out exactly how much to explore in a principled way. And so what we're going to do is apply this inequality to the rewards on our bandit. So what we're going to look at, and we'll just condition each of these on selecting a particular action A, and we'll come up with a different bound for each of our different actions. So we're basically going to plug this in with action value, so this is exactly the same as this inequality. We're now saying what's the probability that the true action value is greater than our estimated action value plus some upper confidence bound u. And we can bound that by e to the minus 2 times the number of times we picked it, times this bound squared here. Okay, so I'm not going to explain, derive this, it's just a well-known inequality. And all we're going to do is now solve for this to figure out what u should be. So what we're going to do is we're going to pick a probability that the true value actually exceeds the UCB. So we're basically saying how sure do we want to be that, that the actual probability is, so there's some tiny probability that this thing is going to be in the tail, that we're really wrong about our mean, and we want to pick a probability that we're wrong about that mean value. So let's say we pick 1%. Well, now we're going to fix that p to 1% to 0.01. We're going to solve for what the upper confidence value should be, such that we're at least 1% confident that, so at most 1% probability we've been wrong about the mean. Okay. So now all we're going to do is solve for u here. So we just take logs and the square root to get rid of this. We end up with this term here. And now the final piece is that we really want to make sure that over time that we really get more and more confident. Remember, we want to make sure that our regret just disappears altogether. And so that means that we need to make sure that eventually we explore everything. To make sure that we explore everything, that means that our confidence bound has to get bigger and bigger. In other words, we need to make sure we start off maybe with like p set to 10%, and over time it will drop to 1%, and eventually to 0.0001%, etc. We want to just make sure that we really have to have the best action with very high probability. So if we set that to some schedule, then you end up with something like this here. So basically what this is telling us is that we should pick our upper confidence bound to be square root of something that basically decays. So this 1 over square root of n term is something like the standard deviation of this Gaussian that we were looking at. And then this log t term is the part where we've got this slow decay over time, more samples. Okay, and this is called the UCB1 algorithm, very widely used, been very successful in lots of applications. And so this is our first algorithm that, without knowing anything about the probability distribution, really achieves this logarithmic regret. So it really gets that nice shape, and we can guarantee that asymptotically you're going to get closer and closer to the optimal value, and so you'll have this nice result. And it depends a bit on the gaps, but roughly it's got sort of roughly the same form as that. I don't know about it, but it doesn't have the K on the dimensions. Okay, so we have an algorithm. Now we're going to talk about some other approaches, but a bit less formally for some of the others. Okay, so let's make this feel a bit more concrete. So this plot here, sort of from the original paper where they derived UCB, and what this shows is two different multi-arm bandit problems. So the first one has 10 different arms. One of them's, and each of those arms is like a coin flip, whether you get a reward of 1 or a reward of 0. And the coins are biased with different values. So one of the coins has a 0.9 chance of coming up heads, the others have 0.6 chance. That's the top plot here. And on this one, we've got 0.9, 0.8, 0.8, 0.8, 0.7, 0.7, 0.6, 0.6 for the coins. So what happens is if you look at this, and this is a comparison of how this UCB algorithm does compared to the sort of scheduled epsilon greedy with this magic schedule. So it turns out that even if you know the magic schedule, that the magic schedule is very, very sensitive to exactly how you tune it. So that's this C value here. So if you get this C value just slightly wrong, you can get this massive regret starting to happen like this. And so this on the second one, which is a sort of hard problem, these three plots here are the regrets for epsilon greedy with this magic schedule, and these two are the two different variants of the UCB1 idea. And it does very, very well, and it's very robust. And you can start to see, so asymptotically you get that curve that sort of looks like the log, but in the short term all kinds of other things can happen. So crazy things can happen in the short term. Okay, so people have done this with other inequalities. You don't just have to do Huffdings, you can do diversities, empirical diversities, Chernoff, presumes inequality, blah, 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 blah. Each one of them leads to a different algorithm for a slightly different setting, and people have basically been working hard to get closer and closer to this lower bound. And they have achieved the lower bound for certain classes of bandit, but there's been a lot of work, it's a very active area on doing this. Okay. So any questions about sort of UCB approach or this regret idea before I move on to a quite sort of different but related approach to bandits. Bayesian bandits now. And the point is that so far we haven't really assumed anything about the reward distribution except this very, very minor assumption, which I hid away from you, that there's the rewards are bounded, which we needed for the updating accounting. So the distribution can be any shape, take on any values, and these UCB approaches are very, very robust. That's what's nice about them. They don't assume anything. But what if we know something? What if we actually have some idea that maybe our reward distribution is Gaussian, or we have some idea what the mean might be, or we know that one arm is likely to be better than another arm? What if we have some prior knowledge? Can we do better? So the idea of Bayesian bandits is to exploit prior knowledge, so to apply Bayes' law to come up with some distribution over rewards, to estimate the reward distribution, and to update that reward distribution by Bayes' law each time we see a reward, and then to use that information to do better. So in other words, what they do, these Bayesian bandits, is they estimate the distribution over the action value function. So there's some action values for each of these actions, and the Bayesian bandits, each time they see a reward, they update the estimate of what QA might be. So they say, well, maybe QA might be high, maybe QA might be low, and keep a distribution over all those things given the rewards you see. And then use that posterior to guide exploration. And there's two ways we're going to talk about to do that, both of which have been quite successful. One of which, again, is upper confidence bounds, and another approach is called probability matching. And so this can really help if the prior knowledge is accurate. If your prior knowledge is wrong, you can actually do worse. So you can, of course, mislead these algorithms by feeding in the wrong information about how the reward function works. Okay, so let's think again, this is our same picture about the upper confidence bounds. So now what we've got here is we're actually going to use Bayes' law to compute these shapes here. So the idea is we're going to use Bayes' law to compute a posterior distribution over the action value function conditioned on the rewards that we've seen so far up to this time step. So basically we're going to be estimating the shape of these things. So it might be that we've got some, we've seen a few rewards for this blue one, maybe we've seen a reward over here, and a reward over here, so now we maybe estimate some Gaussian posterior over this thing. Similarly, we might have seen a few rewards for this red one, and maybe a number of rewards for the green one. And so now we think we've got some Gaussian estimates of the rewards, and the question is, how can we use this now to guide our exploration? And so what we just saw, we can reuse the same idea of the upper confidence bounds, but actually using this, we've now computed this distribution explicitly. So a natural thing to do is to actually use this distribution. So one way to do that would be to say, okay, well, let's compute the standard deviation of these distributions. So we might say, okay, this one has a mean here. The standard deviation, if we add on, say, one standard deviation, it might take us to here. Two standard deviations might take us to here. And we can work out our confidence interval by just adding on some number of standard deviations to the mean. So that's what the C is. It's how many standard deviations beyond the mean we're going to place our upper confidence limit. And so then all we do is pick the action that maximizes the mean plus some number of standard deviations. So we basically say, we don't just pick the action that's the best in the mean, that would be exploitation. We say, okay, well, let's consider two standard deviations beyond the mean and pick the action that maximizes that. And again, you probably want to change this C, needs to grow over time. So it can start off small, and ultimately it needs to capture like the whole distribution if you really want to do this right. So that's the Bayesian UCB approach. So it's quite popular, it works for quite general forms of the posterior distribution. This could be, pick your favorite distribution, Gaussian process or something, but do all kinds of things. Okay, here's a quite different idea. This is called probability matching. So probability matching, basically the idea is to select an action according to the probability that that action is actually the best action. So we've got some posterior distribution, and now we want to use that posterior to figure out, well, now given that information, what's the probability that one action is really better than all the other actions? So we're actually going to pick actions, so this is our policy here, this is the probability with which we're going to pick an action A. We basically want to pick A according to the probability that the action value for A, the true value of A is better than the true value of all the other actions. Okay? So it's a nice idea, sort of this quite clear principle that, well, if I think there's a 1% chance that this action could actually turn out to be the best action, we'll pick it 1 time in 100. And if there's another action that I'm 90% certain is going to be the best action, we'll pick that 90 times out of 100. So probability matching is also optimistic in the face of uncertainty, just like UCBs. And the reason is that if there's an uncertain action, if there's an action which has a lot of uncertainty about it, then it actually has a high probability of being the max. So the more actions there are, the more true it is, actually. So imagine there's like hundreds and hundreds of actions. Each of them has a shape like this. And now, if there's one which has a lot of uncertainty, like this blue one, well, what's the probability that this action is actually going to be the best action? Well, if there's loads and loads of actions, there's quite a good probability that this one will actually be the best action, because there are many times where if we roll the dice for each of those actions, there are many times that the dice will come up saying that the blue one actually had a better value than the red one. And if we took a sample from each of these, there's a high probability that the sample for the blue one will come up the highest. Yeah?
So if we're talking Gaussian, then there's also the same, on that graph, the same probability it will be the worst?
Yeah.
Does that come out in the wash? Or are we just looking at optimal?
It's not the same probability that it would be the worst. You could also compute the probability that it's the worst.
So I mean, it's still got the highest probability of being the worst.
Yeah, so we don't care about the probability that it's the worst. We don't really mind if we waste cycles on things which turn out to be terrible actions. We just want to make sure that we find the best one. So this blue one, yes, it has a very high probability of being a terrible action. But what we care about is the chance that it's actually a really good action. And so we'll choose to invest a few more trials on this blue one just to make sure that it really is a terrible one. And the moment if this thing shifts over to here, then we won't spend any time on it anymore. But we just want to exclude the possibility that the blue one actually is somewhere over here. If the blue one's mean really is over here, we really want to keep trying it until we prove. So the idea of all these optimism in the face of uncertainty is you try the best one and then that narrows the distribution for that one. So you try the blue one, and then if you try the blue one and it turns out to be bad, well, that will change the shape of your distribution to have much less of a tail over in the side region, and then you just won't try it again, because you'll immediately see, oh, actually, this is a bad action. So what we really care about is the chance that these turn out to be good actions. We want to take things that have a good chance of being the best action. We want to take those things more. Okay, so we want to select actions according, so the probability matching heuristic basically says, actually figure out the probabilities that these are the best actions. And so the more uncertainty there is in an action, the higher probability it has of being the best, and so probability matching works quite effectively to narrow down this. It does exactly that property where it will end up trying these uncertain things like the blue ones until they become either turn out to be good or turn out to be bad, and we resolve the uncertainty, and now we know whether it's a good one or a bad one. If it's a bad one, we don't have to do almost any more cycles. Okay. The problem with this probability matching is actually this computation, if you try to do it analytically, can be quite hard for many distributions. For Gaussian it's okay, but actually for many, we want a general approach that can just work quite well. And it turns out that there's a really simple idea that works very effectively to sort of implement probability matching in a sample-based way. And it's really worth knowing about, and it's called Thompson sampling. And the idea of Thompson sampling is basically, it's just turning into an algorithm the thing which I just pointed out with my magic wand there. And the idea is we have some posterior distribution, and we use Bayes' law each step. So each step we pull some arm, we see some reward, we update our posterior distribution over the action value function. So imagine that we've got some parameters, theta, which might be the means and variances of our different arms, or could be any parameters we want for our posterior distribution. But what we're going to do is we're going to sample from this distribution. So we can think of this as like a distribution over different worlds. So these thetas represent a whole bunch of different worlds that you might be in. So if we come up with distribution over, you think that there's one world in which this action is good and another world in which this other action is good. We've got all these different worlds, each of which assigns values to all of the actions. And so what we're going to do is like kind of sample one of those worlds. We're going to pick one of those worlds and say, okay, well in one of those worlds there's some actual value for each of those actions. We're going to just sample that from our posterior distribution. So we're going to sample the action values from this distribution. And then what we'll do is just select the action that maximizes that particular sample. So in that one world, it's going to turn out that in that one world, there's one action which is better than the other actions. And so we just pick that action. We only, just from our one sample, we pick that action. And it turns out that this simple idea actually implements in expectation the probability matching idea. So it's just like I was saying when I was waving my wand here, that we sample something from the blue one, we sample a value from the blue one at random, maybe it's here, we sample something from the green one, maybe it's here, we sample something from the red one, maybe it's here, and then we just pick the action with the maximum value of those samples. And it should be fairly clear that if we do that many, many times, that on average we will pick with probability according to the probability that these things are really the best. Okay, so we're just doing a sample-based way of doing, it's a sample-based approach to probability matching. And surprisingly, this is actually the oldest idea in the whole of the history of bandits and exploration versus exploitation dynamic. It dates back to 1930. And surprisingly, it was only this summer that someone finally discovered that Thompson sampling actually achieves the lower bound on regret that we started with. So this very, very old idea turns out to be very, very effective. So this is true if you start with like a uniform prior. So if you start off with no prior knowledge, and then you do this sort of very naive, simple sampling strategy from your posterior, then at least in the basic bandit setup, coin flips for rewards like we're looking at, this really achieves this lower bound on regret. So it's an amazingly simple algorithm that's very, very effective. And people have tried this in practice, and it seems to do better than the UCB approaches that have been very popular until recently. So it's worth knowing about, and it also has the advantage that if you do know something about your distribution, you can put that into the prior, and then do Thompson sampling with respect to your posterior. It takes account of what you already knew about the world to start with. Okay. So it's worth knowing about. Okay. So one more topic for the basic bandit strategy, and then we'll move on to sort of scaling up to other scenarios. So the final idea which I wanted to bring up is something which is called the value of information. And so this is now trying to make explicit the idea that of why we explore. Like this is doing like the look ahead aspect of thinking, well, I could take this action to figure out whether that action's good, and then after that I could look at this other action, and then after that I would have a really good idea of which of those was the best, and I would expect to get this amount of reward as a result. So really doing some look ahead, taking account of the value that you gain by collecting information. In other words, exploration actually has a concrete value associated with it if you start thinking about the long-term look ahead value. So we call this the value of information. And the question is, can we actually quantify the value of information? Can we say exactly how much is it worth to explore a particular action that we haven't seen before? And one way to think of this is to ask the question, how much would you pay in order to have that information before you make the decision? So if you're prepared to pay £10 to have this piece of information about how good this arm was on this bandit in the casino, that indicates to you that what the value of that information is. So if we can quantify that, we can actually use it to decide when to explore and when to exploit. Another way to think of it is that it's the long-term reward after getting that information minus the immediate reward that you get. So it's like how much value we've added by collecting the information minus the amount that we got just by pulling that arm at that moment. So some long-term value to collecting the information. That's what we want to quantify. So the less we know about an arm, the more we gain by exploring it. So the information gain, the value of information is higher when we're in an uncertain situation. There's an arm that we pull that we don't know much about. So we want to explore those uncertain situations more. And so what we're really looking for now is the optimal way to trade off exploration and exploitation. So we're really asking the question, what's the optimal sequence of actions that we can pick so as to really perfectly trade off exploration and exploitation? And so it's a reasonable question to ask, and can we do it? So the way to think about this is that until now we've viewed bandits as just these one-step decision-making problems. I was saying, well, they're simpler than MDPs. But now we're actually going to turn them back into MDPs again. We're going to view them as sequential decision-making problems, where there's at each step you take an action, and that action actually changes your state because it changes the amount of information you know about the arms. So what we're going to do is think about this big state space that we call the information state space. And each step is going to be an information state that sort of summarizes everything that you've seen so far. So the information state might be something like, well, I pulled this arm 10 times, and on 7 of those occasions I got a reward of 1, and on 3 of those occasions I saw a reward of 0, and I pulled this other arm 5 times and I got some rewards of 1s and 0s, etc. So your information is something that summarizes all of what you've seen so far. Is your information state. So what we're going to do is now formalize this as like an MDP over information states. That when you pick an arm, it doesn't just give you reward immediately, it changes your information state. You find out some more about the world by picking that action, because we've added information. And so we can actually write this out as an MDP. So there's some transition that takes us from some information state. So we take our action A, and it takes us from some information state to some new information state where we've found out more about the problem. So we end up with this augmented MDP of the information space, which we have our information states, we have our original action space here, we have our transitions, the thing which transitions us from one information state to another information state. This is how we find out about information. And we have our original reward function. So this is our way to write this out as an MDP. So we've turned our bandit problem into an MDP. And if we can solve this MDP, then we're done. We really have the optimal way to trade off exploration with exploitation. We've quantified exactly how much it is worth to pick a particular action. So this is very miniature, but I hope you can just about see this. So this is just an example from, so a classic multi-arm bandit setting is deciding, it's like the medical scenario, trying to decide which drugs to give to which patients. And so you basically have, you have a patient, imagine there's just one patient, you need to decide whether to give them drug 1 or drug 2. And here we're saying, okay, well maybe we've got some a prior that tells us something like, okay, and we're going to assume that the drug either succeeds or fails for each of these. And we don't know what the probability of success is, but we've got some prior over that probability. So here we start off with a uniform prior, so we've got some beta distribution, something telling us what's the probability that this coin that we flip will come up with a success and save the patient, and what's the probability it will come up with a tail and kill the patient. It's a very serious drug. Okay, so here we're going to start off with a uniform prior. We've got something where we think the mean of this one is somewhere over here. Okay, and the question is, how should we explore and exploit in this particular problem? I guess once they're dead, we can't really do anything with them, so it's not the best example. But imagine we have a pool of identical individuals who we can keep just giving the same drug to. Okay, and so now what we're going to imagine is what happens. So this is all now sort of in the agent's head. This is like doing look-ahead planning. So we're saying, okay, well, we could give our patient drug 1, and now we know, basically, that we can flip a coin, according to the probability distribution that we have. We can flip a coin, and we know what the success probability will look like, and what the failure probability is, just by sampling from this thing. So we know that there's a uniform chance that the coin will end up saving them or killing them. And so we know that there's some chance that will lead to a success under our model, under our assumptions, and some chance it will lead to failure under our assumptions. And now what we can say is, Well, if it succeeded, we would have a new piece of information. We would move into a new information state where we've seen like one more success. And so we could update our posterior distribution based on that success, and we'd end up with something which looked like this now. So we'd say, okay, well, there was a success, so now we're going to skew our probability distribution from being uniform over towards the successful outcome. And now we could imagine, similarly what happens if there was a failure, we would skew it the other way. And we can look ahead one further step and say, well, if we skewed it that way, we could either then take drug 1 or drug 2. If we took drug 1 and it was a success again, we'd sort of skew it even further towards the successful outcome. If it was a failure, well, then we've seen one success and one failure after our uniform prior, so we'd end up thinking of something like this. And so we can start to do this look ahead of saying, under our beliefs, what would actually happen? Start to imagine all the different outcomes, and at each step we sort of say, well, if our model's true, when we take one of these, how would we update our model? And do this look-ahead planning, where you can look ahead and really figure out how your information would update your beliefs about this problem. And then the question is, now we've got this big tree, how do we really use this tree to figure out the best action to take under our assumptions, with these prior assumptions about how the world works. That's sort of the idea. Does that make some sense? Slightly. This is probably the hardest idea to grasp, isn't it? Well, I think so. Okay, so let's take a particular example. So we'll consider a Bernoulli bandit. So I was talking about coin flips. So let's make that concrete. And so we'll try that one. We're going to have a reward function that's basically going to be Bernoulli with some mean. It's just a Bernoulli distribution, just a coin flip with some parameter mu a representing the bias of that coin. Okay, we're going to have a different bias for each coin. And now we're going to win or lose a game with some probability mu a for each. I don't know why I just did that game. I think that game's too much. We want to find which arm has the highest mu a. So for each of these trials, we want to find, we're either going to kill or save the patient, and we want to find out which arm has the highest one. And so the information state here is basically going to be these two parameters, alpha and beta, which sort of are counting the number of times that we've seen successes and failures. So basically how many times have we saved the patient, that's this beta parameter, and how many times have we killed the patient, that's this alpha parameter, every time we tried action A. And so if we count these for each of the actions, then that summarizes all of the information that we've seen. It doesn't matter the order in which it happens, we just care about how many times we've killed and saved patients by giving them these different drugs. So that's the information state. And now we know that we've got this MDP, let me just put it up actually. Yeah, so we've got this MDP where okay, I guess all I wanted to say is that we not only do we know the information state, but we also somehow we know how that information state gets updated. So if we were in a state where we'd seen some number of counts where we killed the patient 7 times, and then we took the action of actually trying that drug again, then we can estimate what the probability is that we would save or kill them based on our model of what we've seen so far. Okay, so what we've basically turned this into is a gigantic and infinite MDP over information states. I'm good at MDP, we can solve it by reinforcement learning. We could use model-free reinforcement learning, which is an old idea, very called Duff. We could use something which we didn't have time for this, model-based reinforcement learning, which we'll talk about in a second. If you use model-based reinforcement learning, it's called Bayes adaptive reinforcement learning. So what this really means is if you start with some prior distribution, how can you find the Bayes optimal? That means the optimal exploration-exploitation trade-off with respect to your prior distribution. That's what it means to be Bayes optimal. Okay, so in this case, if you're Bayesian, it would mean that you have a beta distribution. So you have some distribution which is basically telling you what's the mean of your coin, given the number of times you've seen success and failure outcomes for that particular action. So that's going to be your prior. You start off with this prior that says, well, it's just as if I start off thinking this drug is going to kill someone 7 out of 10 times, and then we sort of start to explore. And each time the action's selected, we're just going to update this posterior. So if we take action A and it actually saves the patient, we would increment this one, and if it kills them, we would increment this one. So if the reward is 0, the other actually kills them, then the alpha gets incremented. If it saves them, we increment beta. And so this gives us our transition function for our phase-adaptive MDP. We know the phase-adaptive MDP now. We've got our beta distribution that tells us how likely it is that we're going to save or kill them, and if it does save them, we'll go this way, and if it kills them, we'll go this way. Okay. And if we can solve this, then we really will be taking account of the value of information. So it looks something like this. So now this is the same look-ahead tree that we had before. Now all we're looking at is the actual states of this phase-adaptive MDP. So the state is basically, ignore what it says before the code. This is like the augmented information state at each of these nodes in the tree. So you start off with some parameters alpha and beta for each of your drugs, and then we're just going to consider what happens if we take the action of taking drug 1 or drug 2. If we take this drug 1, then this is the probability under our model that we will end up killing the patient, and this is the probability that we'll save the patient. So it's just alpha divided by alpha plus beta. And then according to that, we will just update the counts in our distribution to either update the counts for the killing or the counts for the saving, and then we do that all the way down this tree. So we've created an MDP, it's a big MDP, and we want to solve this MDP somehow. And it turns out there's a very famous algorithm called Gittins indices, which basically we can think of as the dynamic programming solution to this MDP. So the Gittins index basically comes up with a number called the Gittins index. It's basically the value function for this MDP, and it's the action value function. And if you know the action value function for this, it tells you how to pick the actions correctly. So Gittins was the first person to notice that you could do this by dynamic programming to figure out some nice properties of it. But it's very hard to do this. I mean, this MDP is big. Even in the simple case with bandits, it tends to be intractable. So solving this thing exactly tends to be a very hard problem. So people tend to approximate it. One thing we've looked at recently is actually how to apply things like Monte-Carlo tree search to solve these phase-adaptive MDPs, and actually that gives state-of-the-art performance for the exploration-exploitation trade-off in interesting problems like MDPs and so forth. Okay. So the basic idea of that is to say, okay, well, we've got some look-ahead tree. Well, let's use some sample-based approaches to look ahead to solve this rather than do dynamic programming, which blows up very quickly with a branching factor. Let's do something based on simulations and break the curse of dimensionality by sampling, as we talked about in the previous lecture. Okay. So that was quite a talk. We've covered quite a lot of quite different ideas for how to deal with the exploration versus exploitation dilemma. So it's probably a good idea to just maybe pause there, and maybe we could just recap the methods. So the methods we looked at were, well, we started off with these naive approaches like epsilon greedy, which is what we looked at so far previously. We saw that doesn't really scale up to a very effective method. And so we looked at the more sophisticated approaches based either on these very robust upper confidence bound approaches, which sort of use statistical ideas based on inequalities to compute a very robust upper confidence bound. Now pick the action with the best upper confidence bound. So optimism in the face of uncertainty. There are Bayesian approaches which use Bayes' law to update a distribution over the values of those arms, and then you can also either then compute a UCB, an upper confidence bound, using that posterior, or we also talked about this probability matching idea. You can do something like Thompson sampling to pick actions with probability of their best. And then finally, we talked about these information state ideas, where it really starts to look ahead and start to figure out really what's the if we could plan ahead and do this sequential planning and figure out the best actions one after the other, what's the best that we could do? Can we actually figure out the optimal sequential strategy for exploration versus exploitation? Quite different, but all of them quite widely used. Okay, so let's scale up in the remaining time. So we have 20 minutes. So I think what I'll do is I'll give a flavour of contextual bandits, and I won't do a lot of detail on the contextual bandits. And I'll just spend a little bit of time on the MDB case at the end. So what's a contextual bandit? So now we're going to augment our bandit problem to have states again. So we're going to have some actions, some states, and some rewards. So this is like the advertisement banner problem, where someone comes in, some person comes into the website, and you want to show them an advert, but you've got some information about who they are. So you know that this is someone who lives in New York and has visited this website 12,000 times before and has spent a lot of money and clicked on a lot of things or whatever. So which advert can show them? And so you have your arms, and now we have some distribution over who the people are coming into this website, the contexts, the states, the distribution in states, and we want to have an unknown problem. There's some distribution over rewards now that depends on the states as well as the action. And again, this is unknown. And similarly to before, at each step, the environment generates a state. So this is new, the environment now generates a state. So this is like someone comes to the website. The agent gets to select an action, like what to show, what value to show them. And the environment generates a reward. And again, the goal is to maximize the cumulative reward. So essentially the question is how to exploit this state information. Now, if the state space is small, maybe you've got just 10 different states, then everything we've seen before can still be applied, and you can sort of solve each state separately and find the action value for that state separately from the action values for other states. In general, that's not a very tractable solution for interesting problems such as this one. So we're going to look at ways to exploit functional approximation to generalize from one state to the other. And the basic idea is to do it by linear regression. So we're going to use linear functional approximation as sort of the canonical example. So again, this is not the only way to do this, but just like earlier in the course where we looked at linear functional approximation for reinforcement learning, here we're going to look at linear functional approximation as kind of like a standard, sensible, straightforward approach to solving this problem. So first of all, let's define the action value function. So this is now very similar to what we had in the full reinforcement learning problem. It's the value, the expected reward, conditioned on both the context, the state, and the action that we pick. Now it's just the immediate reward, unlike the full RL problem, because this is like a one-step MDP. That's the way to think of these problems. We pick one action, we get some reward, or we don't get some reward, and then we're done. And we just get presented with someone new, some new context, we get to pick an action, we get some reward, we're done. There's no sequence, we don't get to change the state about what we do. That's what differentiates this from the full MDP problem. We don't get to control the states. They're just given to us. So we can't affect the future beyond this immediate reward. Okay, so we're going to do the same trick we did before, where we're going to estimate this value function by a linear function approximator. We're going to estimate this q by this q theta. Now we're going to come up with some parameters theta, and so the choice we're going to use is we're going to take some features of the state and the action. So this could be like features telling us who this person is, might be features of the state, or features of the action might be things like what kind of banner are we planning on showing them, or we might have some combined features of both the person and the banner, so we can figure out what particular banners are appropriate to particular people. We're just going to take a linear combination that says how good those features are, how much they contribute to the value of that particular state and action. And then we're just going to do least squares regression. It's going to be the way that, so this is linear regression. We're going to try and, we've seen some data, we've seen some calls of various different actions for various different states. And we want to estimate our action value function from all the examples we've seen so far. So if we've seen a bunch of rewards, then we can basically do linear regression So it's a standard linear regression just to solve and find the parameters that give us the best fit to the rewards we've seen so far, the least squares fit. Okay? So you should be familiar from supervised learning. And then a popular approach is to basically, in addition to computing the mean, so this is basically estimating the mean, this q theta, you can also, there's a form of linear regression, so linear regression, you can also compute the variance of your estimate in addition to the mean. And so standard least squares regression estimates the mean action value. We'd also like to estimate the variance of the action value function. And if we know that, we can do something like the upper confidence bounds approach. So we basically want to use the variance to give us a UCB that we can add on. So if you think of this as like, we've got some estimate of the parameters, but there's some uncertainty in our estimate. We want to add on a bonus for the uncertainty, what we're going to add on. For example, if we estimate this variance sigma, we're going to add on some bonus. We're going to pick the action that not only gives us the best mean, but the best mean plus some bonus for uncertainty. So the more uncertain we are about parameters, the more we favour the parts of we want to favour parts of the action space that we haven't explored very much, and find out more about them. We want to reduce our uncertainty in the parts of the action space that we haven't explored very much. So that basically means if there are features, for example, that we haven't seen very much, then we're quite uncertain about what the parameters are corresponding to those features. So we should prefer to try those features more, so sort of favour actions. Maybe there's like a class of actions that we haven't tried, like red banners. We haven't seen very many red banners, and so we might choose to favour those red banners because they have higher uncertainty, and we really want to figure out whether red banners are good, because we haven't seen them very much. So we sort of add on this bonus that favours uncertainty, and again we do that in the same way that we saw before, where we could add something on. For example, the Bayesian way would be to add on C standard deviations above the mean. So if we can compute this variance, then we can compute the upper confidence bound by adding a certain number of standard deviations on. I don't think I'm going to go through the way to compute it. I will skip that. It's in the slides if you're interested. What's maybe worth spending just a moment on is this. So this is an example from a major application of contextual bandits to, so this is Yahoo, before Yahoo research exploded. They had this big project where they were looking at basically trying to select the news story to show to people who visit Yahoo. So everyone who comes to Yahoo, they're presented with a news story that's personalised to that person, and they want to basically show people news stories that they're most likely to click on. So they basically show you the headline, and they want to show you headlines that you're interested in, and so they want to basically maximise the probability that you're actually going to click on the news story that they show you. So this is a contextual bandit problem, just like the banner thing I was talking about. But depending on who you are, if you're someone who shows a lot of interest in financial stories, they want to show you headlines that are related to financial stories. If you're someone that shows interest in sports stories, they'll show you more sports headlines. And they figure that out dynamically, and they treat it as a bandit, where they really want to make sure that they don't just exploit, they don't just show, because news stories are coming along all the time, and they need to figure out are these news stories good or bad. And similarly, they don't just want to explore, they don't just, it's no use finding out more and more information about which is the best story. They really want to satisfy their customers in the meanwhile. And so the basic message is that you can do quite well with this UCB approach where you compute this upper confidence bound. And I'm not sure how much I want to go into the details, except to say the messages are this sort of plot, so they basically show how much better than random you can do. So this is like 50 to 60% uplift in terms of the amount of times that people actually click on a news story compared to showing them random news stories. And you can use a variety of different choices for how you compute this upper confidence bound. And it's quite effective across different choices for how you compute the upper confidence bound. And it does a little bit better than epsilon greedy, but surprisingly, the naive epsilon greedy algorithm does actually quite well on the linear bandit setting. So the story is you can be a bit cleverer, but actually the naive approach of epsilon greedy is quite hard to beat for these contextual bandits. But you can do better. Okay. And I just wanted to finish with like you can think of this as like a brief survey of how we can take the ideas that we talked about in the main part of the multi-armed bandits section and how we can then apply them to full MDPs. So, first of all, the upper confidence bounds approach. So the upper confidence bounds approach can be generalized to full MDPs. And the way that looks is something like, we basically have now, we've got our action value function, but the idea is that now we basically say, not only do we estimate the action value function the way we normally do by policy evaluation, so previously in RL, we figured out what's the expected reward given a state of an action. But we never said anything about the uncertainty of that estimate. So now what we do is we track the uncertainty of that estimate as well. We say, okay, I've got my action value function, but I've also got some uncertainty about whether this is a good or a bad estimate. And where we're most uncertain, we add on some bonus. So we want to add on an upper confidence bound that basically represents how sure we are about this action value function. So in particular, if there are states and actions that we're very unsure about what the value is, either because we haven't visited that state in action or because it leads to parts of the state space that we're very unsure about later, there should be a high bonus here. The upper confidence bound will be large, so there'll be a lot of uncertainty there. So it's the same idea we saw with the bandit, just now we've got this for the full action value function instead of just QA. So the simplest example of this was called interval estimation. It's a very old idea, and that was just for the table lookup case. And the idea there was to estimate not just a mean, but an interval for each action value. So for each state S and for each action A, you basically maintain an interval such that you're sure that the action value lies within that interval. And then you basically pick the one with the higher top end of the interval is the action you actually pick. You pick the one with the maximum confidence. Okay. So that was model 3 reinforcement learning. So this is how to do upper confidence bounds for model 3 reinforcement learning. What if we want to be optimistic in the face of uncertainty when we do model-based reinforcement learning? So we talked about model-based reinforcement learning in the last lecture. And so here's one way you can do it. So you can construct a model of the MDP. So remember the idea of model-based RL is you first learn a model, and then you solve that model by planning. Okay? So what we're going to do is the same first step. We'll construct a model of the MDP. But then the idea is we're optimistic in the face of uncertainty, and that we say, okay, well there's some parts of this MDP that we haven't seen very much yet. So basically replace the transitions that you haven't seen very much with transitions to heaven. Like imagine that all the things that you don't know much about actually lead you to heaven. And then solve for that MDP. Okay? And that's going to encourage you very strongly to try the states and actions that you haven't seen yet, because you think they're really good. Or you'll start to find ways to get to those unexplored states in your MDP. And then you try them, and then presumably they don't really lead you to heaven, and so there you'll get a slightly more realistic estimate of their value. And now you can sort of iterate this procedure until you really figure out this procedure leads to a very systematic exploration of the state and action space. So it's a way to systematically make sure you explore everywhere. It's a bit hard to scale up to, so basically, you need to be very optimistic in the face of uncertainty and believe in the best case. So this gives you very systematic exploration. In some cases, it sort of almost explores too much, in that, particularly once you've got function approximation, you really want to make sure that you don't always want to just explore things because it couldn't possibly lead you to heaven. You want to start to make a reasonable guess about what the best you could do is there. Okay, and the way that you actually solve the MDP, well, that could be any planning algorithm. So it could be policy iteration, value iteration, tree search, task search, whatever. Okay, so this algorithm is called, it's actually called RMAX, this basic approach. Right, so, and then briefly I just wanted to mention that In just the same way that we looked at the look-ahead idea, where we started to have an information state in the banded case, we can also augment MDPs to include the information state. So the way that we do that is we augment the state. So the information state, the augmented state, is now a real state that you're in the MDP, plus all the information you've seen so far. So we kind of take a state that's much, much more complicated. We say, not only is the agent in this particular place in the room, but it's also seen all this stuff in the past. And it's got some summary of that information we've seen so far. And this gives you a much, much bigger MDP. And you can now solve for this very, very large MDP. And so one way to do that is to be Bayesian. It's not the only way. And the summary that you use of all the information is a posterior model. So you can update the posterior over models given all the information you've seen. And that's called Bayes adaptive MDPs. Okay, and so this is a very, very large planning problem. So it's hard to solve, but it is possible to address these problems. And what does it mean to solve the Bayes adaptive MDP? Well, again, it means finding the optimal strategy for exploration and exploitation with respect to your prior knowledge. So you have some prior knowledge about about what the world looks like, about what this model of the world is. And now you want to say, well, what's the optimal way to explore, given that you maybe thought something about the world before you started. So this is useful, for example, if you want to make sure that you don't crash your helicopter by exploring the whole state space. You might start off with some prior knowledge saying that moving your helicopter into a large stationary object will lead to a very large negative reward. And so you might have that as a prior in your problem. And if you have this prior there, then now you want to solve the exploration-exploitation dilemma, and this will make sure that you explore the parts of the state space that don't lead to crashes very effectively, but that you avoid the parts where you have some prior knowledge telling you this is almost certainly a bad idea. But these things are big, and it's hard to do, so you typically need to do something like simulation-based search approaches to deal with this very large state space. That sort of recent work. Okay, so that's kind of the end of the tour of exploration versus exploitation.